Okay, so Anil had asked about the syllabus for the course, and I think what I might have done under the requirements is skip the section on grading. The way it works is really simple. Everything counts for a third. Homework counts. It's so important that you keep up with the class. Homework counts for 1/3 of the course. I might be doing perhaps as many as 7 or 10 homeworks, and that's like 33 1/3 of the percentage of your course grade right there. I'll do a midterm as a project, so that means that you all will be able to work on it at home. You'll probably get a week for your midterm. You get 2 weeks for your final. You're going to have to do programming for your homeworks. You're going to have to do programming for your midterm, and you're going to have to do programming for your final. So it's all programming. I'm not going to do any of this memorization stuff. We're going to do applied, hands-on stuff. And so you'll have assignments, regular programming assignments, and let's see, what else do I need to know?
You said you'd be using Java in the class when we do the assignments.
Yep, you can use any, yeah, I went over that in the beginning of class, any language you like, but I'm going to use the language I like. And if you decided you needed to use like MATLAB or what do people use? Ruby. You want to use Ruby? I'm excited. Use Ruby. That's great. I love it. I've never done image processing in Ruby, nor do I know anyone who's ever done any image. So you know what they're very big on now is Scala. Scala is a language that's supposed to be the thing that replaces Java, the next big thing. And it runs on the Java virtual machine. I'm skeptical. I think it's possible that it will work. Anyway, I know that they're hiring people down at, like, in the finance industry in Manhattan who have good Scala skills. So that makes a difference. Maybe the NASDAQ folks will use Scala soon. I don't know. Has anyone gotten in touch with you from NASDAQ, Kyle? No.
They're from somewhere else.
Okay, we'll talk later. So, yeah, it turns out I know people who are hiring, and if you're looking for a position, let me know, and I'll do my best for you. Sometimes I can help. Let's see, what else? All right. So for the lateness policy, I've been doing 10 points per day late, with homeworks due at the beginning of the semester. So it's I'm sorry, at the beginning of the class. So I want So all your homeworks are due now, and that's it. That way I don't have to grade them every day or anything. So 10 points per day late. If you're going to miss something important like a midterm because you're traveling for work or whatever, we'll make some kind of an accommodation so that you can hand your midterm in early. And that way you don't have to have it handed in the same day as everybody else. If you're going to do something like, I don't know, miss a final, that could impact your grade dramatically, so don't do that. I've had students actually flunk because they didn't come to the final. What were they thinking? They had a chance, right? They had a chance to pass the course. They just blew off the final. Not cool. So there are certain things that may actually help you a lot, especially if there's a demo involved. If you don't want to record your screen and upload some sort of a video, you can come to class and demo your midterm or your final, and it might make it a little easier for you. Especially if you're a distance learning student. So that's kind of an interesting way to approach the course. I suppose I could have made it a pure lecture course where all I did was assign problems out of the book. That's doable. I mean, that's how most people take their image processing courses. I got a few different image processing, I'll call them frameworks or systems, available to you. One is under j2d.gui.main. So the first one I showed you was ip.main, and that was the first image processing program, a major image processing program that I wrote, and it was the one upon which the book Image Processing in Java is based. The second one I wrote is called j2d.gui.main. Well, that's probably not what it's called. That's just where it is. It really does need a name. The first one is called Kihindu. And Kihindu is the name of a village in Kenya that has a very fine AA coffee. It's a kind of Java. It's a Java illusion. So here's the thing called Image Tool, which is not Kihindu, and that's in the j2d.gui.main. And they always have, I will call them, innocuous-looking graphic user interfaces. File, edit, process, window. So simple, right? But then when you go down to something like process and you see, there's a histogram, and you see there's a hierarchic menu involved. And the hierarchic menu treatments can go and walk across the screen in a rather lengthy sort of fashion. So what they do is they give you an opportunity to write rather large interfaces. And here we have a bunch of hierarchic menus named after the students. So these are the things that were implemented by students. And so students, here's mine, can have all of their menu items, and then you can write meta menu items. Meta menu items take prior menu items and reorganize them with new graphic user interfaces. So when you want to show, for example, the buttons that capture all of the prior menu items, you can show the buttons, and now here are all the menu items arranged as buttons. Isn't that cool? So that means you can add a menu item, and then you can get a panel of buttons that give you all the operations that are contained within all of those menu items. And you can see there's quite a lot in there. And organizing them nicely with hierarchic menus really helps out, I think. Let's see what else we got. I have some I'll call them relatively funky menu items, like capturing from a USB camera or a web camera, or here's one, I'll capture from the screen. So what this did was it took a screenshot, and now it gave me sort of like this nice little thing. I don't need a camera for that. And now I can go through and I can do the sort of, I'll call it color quantization with median cut. And when you do that, median cut will allow me to reduce the number of colors using the median cut algorithm. So here we'll go down to 256 colors, now to 128, then to 64, then to 32, 16, 8. Now you can see some modeling in here. That modeling is, I'll call them readily apparent visual quantization distortion. And here we are going down to 4 colors. And so quantization error is a characteristic of what process? CDs. A basic signal processing process that is characterized by quantization error. It has a name. First you do sampling, then you do quantization. And we call that it's called digitization. when you digitize a signal, first thing you do is you sample it in time, right? And the second thing you do is you quantize it, right? So sampling it in time means you have a sampling frequency, right? And there's a thing called the Nyquist theorem. Does anybody, I mean, this is like one of those basic signal processing questions. Does anybody remember the Nyquist theorem? I've heard of that. I know you've all heard of it. It's a fun, yeah, half, right? So if you're sampling at 8 kilohertz, your highest frequency should be half, which is 4 kilohertz. Thank you. So if you're thinking about sampling rate, what you're doing is you're thinking about quantizing in time, right? You're taking a, you're saying, I'm going to do 1 frame per second. You're quantizing in time. I'll do 30 frames per second. You're quantizing in time, right? 1/30th of a second. But then there's another part of digitization called quantization, and what that's doing is it's giving you a continuously varying signal and giving you fixed numbers, right? It's converting from floating point to fixed point with a finite dynamic range. So what that means to me, the let's say computer designer who has to design an A to D converter, an analog to digital converter with quantization in mind, is it means there are so many bits that are available. So if you have an 8-bit A to D converter, then you get 2 to the 8 or 256 different quantization levels. Let's say you have a microcontroller like the Arduino, right? The microcontroller called the Arduino has a 10-bit A to D converter, which means it has 2 to the 10 quantization levels. 2 to the 10 quantization levels is 1024. Isn't that right? 2 to the 10? 1024. I think so. So then, right, because 2 to the 9 is like 512, 2 to the 10 is 1024. Trust me on this. I think it's true. So then, what will be the smallest error in quantization if you have a value that ranges from 0 to 5 volts? Because remember, your Arduino runs on 5 volts. And the smallest value you can put in, can't be negative, is 0. So the next step up from 0 is 5 volts divided by 1024. So that is some number, perhaps in millivolts, which will give you your actual, I'll call it, voltage of quantization. Let's look at your calculator, right? And I'll tell you exactly how much that is. Take 5 divided by 1024, and you get a number, and that's about 4.8 millivolts. So 4.8 millivolts is your voltage of quantization in an Arduino with a 10-bit A to D converter, right? And what does this mean to you, the programmer? What it means is you're going to have to deal with a 10-bit number. And if you're normally dealing with 8-bit numbers in bytes, you're going to have another 2 bits rolling around on some other byte boundary, which you're going to have to glue together in order to get a total value. So you can do it a couple of ways. Either you take 2 bytes and glue them together to make 16 bits, and then call that a short. So take your short and use the least significant 10 bits, clear out the most significant 6 bits, because you're not going to use them, and just waste them. Waste those 6 bits. Who cares? And just use the least significant. Later, if you add a 16-bit A to D converter, you'll be all set, because you'll have reserved the space for it. So what this means to me, the programmer, is I need a whole 2 bytes. But if you don't have the space, because Arduinos don't have much memory, you could probably throw out the least significant 2 bits and just keep the most significant 8 bits. And just make an 8-bit A to D converter. But if you do that, you're not going to have a 4.8 millivolt quantization error, are you? What would your quantization error be on your Arduino with an 8-bit ADD converter? What would it be? Yeah, 5 over 256. So what does that look like? Well, that's not 4.8 millivolts. It's more like 19.5 millivolts. Big difference. All right, so you've just increased your quantization voltage, and that quantization voltage represents the least significant quantum that you can register as noise. Because what will happen is when you listen to the noise floor of your A to D converter is it's going to be plus or minus 1/2 the least significant bit. It'll be diddling around that 19.5 millivolts, and that's the noise that's going to come through your speaker and sound like shh when you crank up your sound. So that's going to be really noisy. That's a noisy system, and it won't sound any better than a voice grade telephone line. Probably worse. Probably worse. But that's the trade-off, because now I got only 8 bits to have to store as a programmer. So you can see these trade-offs are coming in. So we've got trade-offs on the sampling rate. We've got trade-offs on the number of bits of quantization. And these trade-offs impact us not just for one-dimensional signal processing, but also for two-dimensional signal processing or imaging. Right? So when we start to think about low-level signals and how we're going to amplify them, it might make sense to have a lot of extra, I'll call it dynamic range, in our imaging sensor in order to be able to get down below that noise floor. So that's why it's sort of an interesting idea. And here we are quantizing to 4 levels. And with only 4 levels, you get a lot of quantization error, and you can kind of see the quantization noise. And this is, I would call it, a very, I'll call it, coherent image, right? There's coherence in image processing, which I would call inter-frame coherence, and then there's intra-frame coherence. Inter-frame coherence means one frame is kind of like the next frame. Intra-frame coherence means the pixels inside of a single image are like the pixels next to it. So when you look at, let's see if we can see, I'll just increase this a little bit. Look at this area in here. All these pixels are the same value, right? So there's a lot of intra, within the frame, coherence. And you can exploit that when you try to build compression algorithms. What somebody might say is, look, there's 1,000 pixels and they're all the same. Let's code it into a single code word and say, here, take 1,000 pixels all the same. Here, take another 10,000 pixels all the same. And you can use this little code word and represent a whole bunch of pixels. Large areas can then be encoded easily. Some people use what's called run length encoding. Here comes 1,000 pixels with this color. Here comes 1,000 pixels with the next color. And that run length encoding can be very efficient as a coding system. So when you start to think about intra-frame coherence, you can think in terms of coding. And you can think about large areas of constant color that you essentially encode efficiently with nice, crisp outlines, because your eyes respond well to those outlines. What do you think of that? So, if efficient intra-frame images, intra-frame coherence can be reduced in with I'll call it median cut 4-level quantization and still look okay, what would happen if it wasn't a synthetic image, not a screenshot? Right? Let's try something else. Let's try and open up yeah, this is a scary looking one. Dr. Diffracto. Ooh. So now Dr. Diffracto there, We can go this to 256, looks alright. 128. It's all looking fine. Is this working? Oh, there it goes. So now at four colors, 4 levels that you can definitely see modeling. At 16, you could definitely see a difference. 32, you can see more quantization. I don't know how good it is with the... I can see it here on my screen. I don't know if you could see it up there. A little bit. I think what's happening is you're getting a lot of low-pass filtering when you run a long wire out to the projector over there. It takes away a lot of the bandwidth. So this is kind of an interesting idea, right? You can take an image processing, and you can rob it of its color, or you can requantize the image, right? Requantization is the operation that you just saw. So requantization takes a color, and then it transforms it to something that has a different number of colors. That's requantization. So here's an interesting question. What's color? What? That sounds like a good question, doesn't it? What is color? RBG or RGB? RGB. Is color the same for you as it is for, let's say, a dog or a snake? Color is color, right? Snakes can see infrared, right? So they can see in the dark. They can see their prey. They can go into these burrows and find little rabbits in pitch black. They can smell with their tongues. That's another thing. That's not color. So if snakes can see infrared, color is sort of different for them than it is for us, right? They have a different spectral range. So what is color? It's about the brain, isn't it? Color is a sensation. It's a sensation created by our eyes, usually, and our brain. And if we had neither, we wouldn't be experiencing color. So there's an interesting concept here. If color is a perceptual experience, a sensation, then how do we stimulate our visual system in order to perceive color? Yeah, how do you see color? Yeah. Well, there's 2 kinds of color systems in common use for humans. One is called additive synthesis, and the other is called subtractive synthesis. In your additive synthesis color system, you paint with light. And so what you do is you add red, green, and blue as your color primaries, and then what comes out is white. So by combining red, green, and blue, you get white. In a subtractive color synthesis system, you take away colors by adding pigments. And so what that does is it uses a different set of color primaries: cyan, yellow, and magenta. And with cyan, yellow, and magenta, you take white paper and you add the inks until eventually you see black. And effectively what you're doing is you're absorbing all of the incident light except for the light that is the color of your pigment. So if you put down green, you're actually absorbing everything but green. And then you reflect the green back. And then if you put down yellow, you absorb everything except for yellow. Well, what some people do is they take equal amounts of cyan, yellow, and magenta, and they do what's called gray color removal, GCR. And they remove it to the black plane because they want to save on the more expensive color inks. So when you go to buy an inkjet printer cartridge set, you buy cyan, yellow, magenta, and black. It's not required that you buy black, but you do it because you can get a reduction in the amount of cyan, yellow, and magenta inks that you use, and also you can get something else from your inkjet printer. You can get a clear outline. You can get clear text. You can get, I will call it, a way in which to avoid rosettes. Rosettes occur because when you have paper and you hit it with ink, the ink takes that paper and spreads. And when it spreads on absorbent paper, it's called what's known as dot gain. That dot gain has to be a function of the kind of paper you use. Some people use glossy paper to avoid the dot gain. And so what you do is you take a little pixel and you change its size and you change the number of dots using a dithering process, and you create a rosette. And the rosette is of cyan, yellow, magenta, and black. And what you can do when you look at any printing process that's color, and that's true also in the cover of this book, Image Processing in Java, take a magnifying glass and look at it really carefully. And what you'll see is you'll see the rosettes. If you go to the tip-ins in the center of the book, you'll see they were printed on 60-pound glossy paper. Those tip-ins are all going to show you rosettes. Now what happens when you have a professional printing press do your printing for you is they will get what they call a line frequency that usually exceeds 133 lines per inch. And so what that means is you get 133 rosettes per inch. Each one of those rosettes with cyan, yellow, magenta, and black will give you at least 8 bits worth of, I'll call it, dynamic range for each one of the colors. So if you think about it that way, you've got, for cyan, yellow, and magenta, 24 bits. Add another 8 bits if you want to add the black. So this is kind of an interesting idea. You're looking at least 24-bit color, at least, when you're looking at these screens. And when you think about it, you're trading off color resolution for spatial resolution. So here is an aspect in image processing which allows us to show a direct trade-off. I could give you improved dynamic range if you will remove the total number of pixels available per inch, because I can make those lines thicker. I can go out beyond 133 lines per inch. Maybe if I go down to, let's say, 64 lines per inch, then I can give you a whole bunch more dynamic range in terms of your color. So that's kind of an interesting trade-off. When they do the printing, they don't print using a laser printer. Instead, what they do is they print using what's called an image setter. And the image setter has an output not on paper, but on film. And what the film does is it allows you to get much higher resolution, because what you're really printing on is a photographic process. This paper, if you will, is really nothing more than film that's being exposed. And you get 2,540 dots per inch on that paper. And then they print out the paper 4 times for cyan, yellow, magenta, and black. And then they take that translucent plastic and they lay it on top of sensitized copper plates. They expose the copper plates and then mount them in a printing press. And that is the printing process as it's done in industry, like at Prentice Hall. Not the same printing process that you get with an inkjet printer at home. But they're printing with mud. They're not printing with light, because they start with white paper and they add pink pigments. And so if they were printing with light, when you add cyan, yellow, magenta, and black, it would turn white instead of black. And so that's the sort of the big thing when somebody says, "What is color?" It's a complicated question, right? Not an easy question. but it's actually a question that's answered in this book. What is color? Yes, sir.
How, I'm just trying to think about it conceptually. How does the computer know what colors exist in a given image? Like, how do you extract that information from an image?
Well, this is a very big question. I used to work for the Jet Propulsion Laboratory, and we had a satellite called Voyager. And Voyager was launched in 1977 with the computing power of what today we would put into a toothbrush, right? I mean, that's how much computing, like an Arduino, maybe a little less. An 8-bit toaster controller. Essentially, that's what the Voyager had. But it had wonderful cameras. And so it would come up to planets. And you were like, okay, here's Voyager taking a picture of these planets. And you're like, all right, what do they really look like? And then the answer is, well, it depends what spectra you're looking at. So in the infrared spectra, here's what you see. But the eye doesn't see infrared. So then the question is, how shall we represent the infrared image to the eye? And so now what you do is you create what's called false color. And so false color, or pseudo-color, takes these values, which may have very high dynamic range. Like if you look at Hubble Space Telescope pictures, you're looking at 12, 16-bit dynamic range for each channel. And the channels are running through spectra that the eye can't see, like X-rays, because X-rays are so important in outer space. And so then the question is, how shall we represent those colors? And then the answer is, well, you do what I'm doing here right now. You create false color. And you decide what would be an appropriate color to use based on your own judgment. There is no set rule. So when you have a sensor that's going into a band that people don't normally see at, and you decide you want to visualize it, you create a color. And you put it on the computer and you say, okay, anybody who comes in with this value has that color. Anyone who comes in with the other value has another color. Go you one better. Sometimes what people will do is they'll synthesize images completely. And when those images get synthesized, it's not clear which colors they should use or why. And you could just use whatever you like. It could be like this artistic thing, or you could say, I want saturation, or you could say, I want it to look like, some sort of an interesting and wonderful thing, whatever that may be. Yeah, call it art. And so that's called a colorization process.
So the machines that detect like X-rays and stuff like that, are they actually seeing these rays, or are they using something that an image that we can?
They're sensing.
So
It's okay to say they're sensing energy, and the energy has a power spectral density. And then the question is, which spectra should be assigned to which color, and also at what intensity. So you have completely orthogonal things, different frequencies and different intensities. And at those different frequencies and different intensities, you may like to be, well considered about how you want to assign your colors. So typically, you could start with a grayscale image. Let's see if I can find one. We'll open up a grayscale image. I think I've got, here. Here's a grayscale image. The baboon. Okay, let's assume the baboon is an image we'd like to color. Well, there it is. Now, I tell you, that was a grayscale image. But what we've just done is we've made it into a completely different sort of image, right? A non-grayscale image. So at this point now, I could say, well, maybe I should do something else. I don't know. Here, let's try the Wu color quantization system. Now we use this on a grayscale image to illustrate that even though there's color quantizations going on, it's going to continue to be a grayscale image, but the number of grays will be reduced. And so now we're down to just a couple of grays, and you can see there's still going to be requantization errors that are visible. So that's an interesting point. You can color quantize grayscale images, and what you're really doing is grayscale quantization. So isn't image processing fun? Very fun. Now, of course, you have all the source code here, but the question of whether or not you want to look at it all at once is another matter. Some of the things that you might like to do might go beyond color. Let's see if we can find something fun. Let's see. Here's the edge detector. We saw that already. I think I've got thresholds. That's good. So threshold is a very simple kind of quantization. What it says is anything above a certain level goes to white, and anything below a certain level goes to black. And so now all of a sudden it becomes very clear the threshold as a global operator is a relatively powerful tool. You change a small parameter and you can see the kind of control you have. You can adjust this over as many pixels as you like. You know, as many pixels and even as many images as you like. And it's all with single slider. But suppose you wanted to do something a little bit more, I'll say, elegant than well, let's see. I'm trying to find. There it is, the contrast panel. So let's change the contrast. There we go. Now we can brighten the image or darken it with high contrast. And now that's still a global operation, but we can make the image somewhat easier to see from a distance when we improve its contrast. So that's kind of like a threshold operation, which essentially just was a two-level quantization. But this is a little bit different. Now we're doing a linear transform, where we're changing the slope and the intercept of the transform between the input pixels and the output pixel. So this is still image processing, but now instead of a single parameter, we're using two parameters. Well, that's interesting. Now suppose I wanted to take this idea about doing contrast and I want to do what's called histogram equalization. Now let's see, here's a thing called a histogram panel. And what it has is the ability to change the exponent of the histogram, again a single slider. So this is an exponential histogram equalization. Or it can do what's called a uniform non-adaptive histogram equalization. And that just works across the entire image and gives you a maximum dynamic range. So then you say to yourself, well, okay, I see the image, I see it changed. How do I know that's giving me a maximum dynamic range? What can I do to measure this image in order to be able to show what the dynamic range is for the red, green, and blue channel? How do I know? How do I know that I've given a maximum dynamic range to this image? Right? What does the dynamic range even look like for red, green, and blue? Well, you can look at the histogram. Now, the histogram is an interesting phenomenon. It is the probability distribution function for a discrete sampled system. And what happens if you take a probability distribution function and you operate over a discrete sampled system? What do you get? It all adds up to 1, but that's true for probability distribution functions, and it's also true for their discrete analogs. So what would we call a discrete probability distribution function? they may not cover this in the probability and random variables classes that you take. They call it a probability mass function. Probability mass function says, okay, how many people in this class are under 5 feet? The answer might be like 1. Okay, how many people are between 5 feet and 6 feet? And the answer might be, I don't know, 4. And how many people are over 6 feet? And the answer might be 1. Right? And how many people are there total? And the answer might be 6. So now what you do is you take those total numbers, like 1 over 6, and you say that's a probability mass function, and 4 over 6, that's a probability mass function, and the other side, 1 over 6, that's a probability mass function. What you've done is you've made an approximation to a little bell curve, but you did it digitally because you had a discrete number of students with a discrete number of ranges over which those students could be measured. And so what effectively you just did was a histogram. And that's all you're doing with an image. With an image, what it says is how many pixels do we have that are of value 0? How many are of value 1? All the way up through 255. We do that for red, we do that for green, and we do it for blue. And then we divide through by the total number of pixels in red, green, and blue. And that's your probability mass function, your histogram, your color histogram for your image. Very simple computation. And yes, when you add up all of the probabilities, the discrete probabilities in the probability mass function, you get 1. But not only that, if you only add up, let's say, half of them, you have a cumulative mass function. In other words, when you integrate a probability, you get a cumulative distribution function. But when you integrate a probability mass function, you get a cumulative mass function. So what that says is, okay, what's the probability of somebody being, let's say, less than 6 feet tall in this class? Now the answer is the number of people who are less than 5 feet tall plus the number of people who are between 5 and 6 feet tall. So you added those two probabilities together and you got a total number which is equal to 5/6. And so now you have created what's known as a cumulative mass function. So you can use the cumulative mass function for the images as well. Right? You can accumulate the probabilities by adding them from here to here or from here to there. You can go from anywhere to anywhere and say, what's the probability of there being a pixel in this range? Add up all those masses, you'll get that cumulative mass function. So now, how does the histogram change if we go back to the original image? Here, let's revert to the saved image. And then what we'll do is we'll go to the histogram and take a look and say, gee, I wonder how that looks in comparison to the other one. We had two, right? Shoot. Here, let's take the histogram panels. There we go. I got these histogram frames sitting around behind one another. So here's a histogram frame. Let's see if we can do the histogram equalization, then apply the histogram, and then look at this histogram, and that looks very different than this histogram. Right? We've spread out the colors. We've given it. We've taken advantage of our dynamic range a little bit better. The image looks much brighter to us. It is a form of distortion, no question about it. Right? But it is also an image that would print much better on a laser printer. It's an image that, when subjected to color quantization, would look much better. So if you go through and requantize the image and reduce the total number of colors, that image, that requantized image, will look better if you've done a uniform non-adaptive histogram equalization first. But notice I keep saying non-adaptive. Right? What would an adaptive histogram equalization look like? What would that mean to be adaptive? What would you adapt to? Right now, a histogram equalization seems to work on the entire image all at once. But if it were an adaptive histogram equalization, it would work on a smaller area and then go to the next area and then the next area. So on a local area basis, and you could make the areas as small as you like. 1 pixel would make it non-adaptive, but you could work on a 4x4 or a 16x16, work on small blocks, and now you can improve the dynamic range for each one of those local neighborhoods. That would be an adaptive histogram equalization, and we can do that too. Although I forgot how that works. That's terrible. How am I doing on time here anyways? Oh, wow. It's almost done. So I kind of wanted to give you sort of fisheye panel. Does that work? Oh, look at this. What could this do, I wonder? Oh, yeah. How fun, right? So with image processing, you get an opportunity to do the kinds of image sequence processing or image sequence outputs that you might not normally have available to you in something like Photoshop, especially because you can write your own. Let's see if we've got some other interesting. Here's the shape buttons. Let's see now. Here's the oil processor. Apply. There. So now it looks like an oil. That's kind of cool. Let's see if the feedback processor works. Feedback. There we go. Now we'll put it a little distance, and then we'll zoom out a bit. How about that dial, huh? I worked hard on that dial. Believe it or not, little things like that matter. The number of iterations we can increase. So now what we're doing, this is kind of interesting, it looks like feedback because what you're doing with video feedback is you're taking the output of a television and you point a video camera at it. You may have done this already. Or if you're sitting in a barber shop, if you've got a mirror behind you and a mirror in front, you'll see your image going off into infinity. Right? This is doing a very similar thing, only I'm adding a rotation and scaling down. So that's yeah, you can increase the number of iterations as much as you like. In theory, this should work for the interesting color image. Let's apply the color image and then go in through here, and now you can see it right there. Now if I had a live camera feed coming in from the video camera, you would see this working in real time with a live video feed from, let's say, well, actually I think there's a camera built into this laptop. I'll have to try that out. Using Java Media Framework, you could stream the video straight from the camera and put it into the image processing program. And that's kind of fun. What I've been working with is static images that are just sitting on the disk. Let's see. We already got the shape buttons shown. So here's a kaleidoscope processor. I wonder if that works. That looks like something. Now I don't know if you've noticed, but I have one frame with multiple little frames inside of it. That's called the multiple desktop tool. And that's another, I'll call that an advanced swing concept. Oh yeah, this is working. It's gotten a little out of hand here. Number of sides. Oh. Yeah, that's, you know what, I think it would work better if it was, there you go, black and white. So that's kind of looking like a kaleidoscope, sort of. Lots of interesting and wonderful effects that we can work on here. I don't know what that does. So what I thought would be fun is if we could assign a little reading from the book, and maybe a little assignment. So for your assignment, I'd like you to download and do a build on the code so that you can have fun with the code on your own. I think that would be fun and educational. For reading, I'd like you to get out to the display and filtering of images, which will get you right out to page 39. So you should be able to read the introduction quickly. What is image processing, that sort of thing. You should be able to get through basic event processing in the AWT. That's the Abstract Window Toolkit. Let's see now. And what I'll do is I'll get you out to I'll call it displaying of images as quickly as I can. But just to give you a basic notion of how that will work, I'll write a very simple program to open up an image and display it using my toolkit. And what we'll do is I'll create a little example here in the under Book Examples. Perhaps we'll do this under Graphics, and we'll call it, I don't know, want to give it a nice name. Make a new class and call it Image Display. And with Image Display, what we'll do is we'll make a oh, really? Control J, PSVM, will create a public static void main method. And what we'll do is we'll go to a toolkit. You guys know what a toolkit is? No. Toolkit is a bunch of classes that are related to a single task at hand that you're trying to use. So I've got a little toolkit which I use for image processing. And one of them, the repositories of all of the methods, static methods that you can invoke, this is like a main, I'll call it keyhole into my system, is image utils. So there's a bunch of utilities called image utils, a whole ton of methods in there, and you can call display image. And display image takes an image and a title, and then it displays it. And so that's good. You got to make sure you got an image, and you're going to give it a title. Hello world, right? That's what everybody says. I don't know why. Why does everybody say that? So now the image is a basic, I'll call it Abstract Window Toolkit data type, just like a string, only it's not a string, it's an image. And we'll set it equal to image, and we'll go and we're going to get an image. And again, I'll use image utils dot get image, and Alt Enter to import. Alt Enter, and there it is. There's your hello world of image processing. That's it. But you want to run it? Why, don't you think this will work? So it should prompt you for an image. Here's an airplane. And then it'll say hello world at the top. Got it? Oh, that's a good idea. Ooh, let's write a program that does that. We could do that. That's a good one. So at the end of the day, an image has a graphics context. So you can go to the image and you can get the graphics context. And the graphics context, graphics, G, equals, has the ability to do a series of things. And one of the things you can do in a graphics context is you can draw a string. And the string can say something like, hello world. And then you can draw it right in the middle of the image, or somewhere close, let's say 50, 50. Those are coordinates, but you got to do them outside the quote. 50, 50. And then it'll actually draw onto the graphics context of the image. And then hopefully we'll see hello world when this gets rendered, but I'm not convinced we will. It might work. I think there's still another step in there. We'll try it. Open. Ooh, he doesn't like that. He doesn't like get graphics? Really? Yeah, I gotta use a buffered image. I had a feeling that was going to happen. Get buffered image. Right? Stop that. This is not my fault. It's because you asked me to do something interesting. Get buffered image. And now he wants an image file. So we'll put a file in there. And let's get a file. So let's do this. Feudal dot get read file. And Alt Enter. No, he doesn't like that? Alt Enter. So that'll be a file. And we'll put a prompt in here that says select an image. And now here's the file. I thought we did this already. Didn't we say Alt Enter? Import class. Okay. Good enough. And now we have a buffered image. I think we can get the graphics context from that. Let's see. If we can't do it. Oh, there it is. It says hello world. Huh? Can you see it? Yeah. It's in white. Oh, you don't like the color? That's okay. We can do that too. So now what we'll do is we'll say g.set foreground. No? Set color? I could have sworn it was... Isn't it set foreground? Just a minute. There's a way to set color. Set. Here it is. It's set color. And now we'll pick a color. Color dot green. No, red. No, green. Okay, green. I don't know if that works, actually. Open. Yep, it's green. Greeny, sort of. So, it's graphics and everything, and you can draw lines and strings and circles and squares and rhomboids and whatever you like. So there it is, image processing. Now, what's the difference between image processing and computer graphics? Nothing. I can assure you there are two different fields and even different courses involved. Just like differences between signal processing and image processing, there's a difference between image processing and computer graphics. Anybody know? We'll end the class as soon as you answer the question. Geometry, excellent. So what happens with the input for image processing, it's an image. And the output for image processing is an image. But with computer graphics, the input is geometry, and the output is an image. So the only thing that's different between image processing and computer graphics is geometry. The geometry is so critical. So now all of a sudden we have, really define the fields based on Not the fact that they're all that different, but that they're all the same, really, except for their inputs and their outputs. And that's kind of an interesting idea. And one more question. What is the difference between computer graphics and computer vision? With the computer vision, the input is an image and the output is geometry. So with computer vision, if you can look at, let's say, a picture of the room and then output the geometry that is used to comprise the room, that's computer vision. So if you can assign symbols to the image, if you can look at an image and say, oh, there's 21 cents on the table, that's computer vision. By outputting symbology or by outputting geometry, you get computer vision. If you look at a picture of a face and you say, that's a terrorist, that's computer vision. If you look at a picture of a fingerprint and you say, aha, that's the fingerprint of a terrorist, that's computer vision. Does it always have to output, yep, that's a terrorist? As a matter of fact, it's a very simple program. That's all it does. So, on that note, you've got a programming assignment. You've got a reading assignment. I think there's probably still pastries in the office. Yes, sir.
Are you going to be doing what you did last semester where you post everything on Blackboard?
Yeah, I'm going to use Blackboard. I'm going to try and see if we can't use Vimeo for the pictures because Blackboard is bad at video. And I'm going to see what I can do to take all the sections and treat them as one when I proceed through the semester so that the distance learning students and the on-the-ground students will all see the same emails. So that means you're all going to have to be able to take your Fairfield University emails and forward them to your favorite email accounts. So if you're a Gmail person and you only check your Gmail, then you better make sure that Mary Kleps, or whoever is in charge of Blackboard, has your emails forwarded to the correct email address, because they will not use a Gmail account in Blackboard. They'll only use the Fairfield accounts. So you can get it forwarded, but you've got to ask for it. That's critical. Otherwise, you'll lose touch with me. And then when there's a snowstorm and class is canceled, you'll be here and I won't. Ha ha. So very, very important to stay in touch with the course, especially if you're going to do distance learning.
Didn't you do something before in digital design where you had groups or something?
Yeah, I was using Yahoo Groups before. I'm not real keen on Yahoo anymore. I think Marissa Meyer has kind of pissed me off. Well, she keeps changing everything, like that Yahoo API that got disappeared. You know how much work it was to get that to work? And now I got to go debug that because she changed something? What was that about? And for what? You know? So I'm kind of bummed about all that. And yes, sir.
Oh, I was going to ask you, did you send that the Dropbox link?
Not yet.
Okay, yeah.
I'm going to do that soon. I uploaded it to Dropbox this morning, and I'm going to send out a link and upload these videos and merge the sections, but it probably won't happen tonight. Probably, like maybe tomorrow or something like that. Tomorrow morning. I want you to do the download and get the image processing program to run. You might like to try and do something like that. But I'd say, this is such a simple program. The thing you really want to do is see if you can get the whole project to build. So if you've got problems building it, bring your laptops with you if you have a laptop, and we'll work on it together. If you can't bring your laptop with you, send me an email and we'll set up a virtual session, and I'll get in using TeamViewer and I'll help you remotely. Sometimes the best time to do something like that is on a Sunday afternoon. Things are quiet. I can just sit at home, get into your system remotely, and we can work through the problem together. That generally helps. So for people who are stuck, don't just stay stuck. ask for help. That's why I'm here. Okay? Have a good evening. Drive safely.
So, also, what about books?
The books are here.
Oh, so
You want to buy a book? I got books.